So today we're going to be going over a composition of functions. Now a composition, one of the big reasons why we learn these is they can be used to test an inverse function. If we compose f of g and g of f, both of x, and the resulting composition is x, then the second function is an inverse of the first. Meaning if we compose this, g, and we get the answer of x, g is the inverse of f. If we do it here and we get an answer of x, f is an inverse of g, which means they're both inverses of each other. So let's try a few of these out. So for the first one, what we're going to do is we're going to try f of g of x, which means I'm going to plug g of x into f. So I'm going to say, okay, my f of x is 5x, and I'm going to leave that x open to plug in g. 1/5 x. And when I work that out, what ends up happening is I get x. So f o g of x checks out. G is the inverse of f. If I try it the other way around, if I say g of f of x, well, g of x is 1/5 x. Let's go ahead and leave that x open for the f, which is 5x, and see where this takes us. Well, 1/5 of 5 is 1, so I'm left with g of f of x is equal to x, so that checks out. So we know that they are each other's inverse. Awesome. So let's try something that's not just multiplication. Let's try something that is addition and subtraction. Let's give this one a shot. So we know that we need to take f of g, so f of g of x, or f of x is x plus 5. So I'm going to set up that, give that x a big room, and stick g in there, x minus 5 right inside there. Well, we know this is going to end up being x minus 5 plus 5, which leads us to x. So f of g of x is equal to x. Boom, g is the inverse of f. But we're not done yet. We need to check the other way around. So g of f of x, take my g of x, so x minus 5, and leave a big old space for that, and say, okay, that is going to be an x plus 5 minus 5. Plus 5 minus 5 cancel each other out, so I'm left with an x. So g of f of x is equal to x, check, check. Again, they are each other's inverse. Awesome. And so we notice that you could look at it and say, well, obviously, if I'm adding 5 and taking away 5, those are the opposites of each other. Of course they'll be each other's inverse. Same thing with number 1. If I'm multiplying by 5 and dividing by 5, of course they're each other's inverse. But what happens if they're not simple one-step functions like this? What happens as we get more complicated? We have two different ways to look at it. I have a 2x plus 1. It looks like I'm multiplying by 2 and adding 1. Here I'm going to be subtracting 1 and dividing by 2. Both opposites, but if I look at this in the grand order of PEMDAS, it looks like I'm going to have to subtract and then divide, where here I'm multiplying and then adding. So it looks like if I were to go according to PEMDAS, they're in different orders. To where if I look at number 7, it looks like I'm multiplying and then I'm subtracting. Here, where I'm dividing and then I'm adding. Both of these cancel out the operations individually, but which order? These are both multiplication and division first, and then addition and subtraction. So these both follow PEMDAS. These go opposite. One multiplies and then adds. This one subtracts and then divides. So opposite of PEMDAS / each other. I'm going to put EO for each other. So we're going to see which way is actually a true inverse. Do we need to go opposite of PEMDAS according to each other, or do we need to follow the same order but make sure we do the inverse operations? So let's give this a shot. So for our first one, our f of g of x, we're going to take our f of x, which is 2x plus 1, and leave a nice big old gap for our g of x, which is x minus 1 all over 2. And what we notice is right here that those 2's cancel out. X minus 1 plus 1, that's going to leave us with an x. So f of g of x checks out. So far, the opposite of PEMDAS, if they go in the opposite order, looks like it's working out pretty well. Let's double check to make sure it works in reverse. G of f of x is x minus 1 all over 2. I'm going to leave a nice big space here. This is going to be a 2x plus 1. Okay, and as we work this out, plus 1 minus 1, 2x over 2, x. So g of f of x equal to x. Boom. They are each other's inverse. So boom. If they go the opposite of PEMDAS slash each other, so these went in opposite directions, they inverted each operation, but they did them in a different order, that worked. Will it work like this? Well, again, there's only one way to test it. Let's go ahead and plug it in. So f of g of x is equal to 2x. Nope, I'm looking at the one right above it. That's going to be equal to 3x minus 7. I'm going to go ahead and leave a big space right here and say that is 1/3 x plus 7 and see what we get. Well, we have to distribute that 3, so that's going to leave me with an x plus 21, which is an x plus 14. So f of g of x does not work. So g is not the inverse of f, but there's still a chance that f could be the inverse of g. Let's go ahead and try this out. So 1/3 x plus 7. Leave big old room inside x to plug this. It's 3x minus 7. I'm going to have to distribute this 1/3, so that's going to be an x minus 7/3. Well, if I converted that to thirds, that'd be 21/3. So 21 minus 7 is going to be 14/3. So boom, f is not the inverse of g is not the inverse of f, neither are each other's inverse. So we made a key point here. If we have opposing operations, addition, we must see subtraction. If I see multiplication, I must see division. But the big key concept is they must be in opposing orders. If I follow the x on my way out, multiply and then add, I'm going to have to reverse that and say, well, first I'm going to subtract and then I'll divide, which is exactly what we see here. The x is subtracted, then everything is divided. Here, looks like if I follow my x out, I multiply and then I subtract. Here, I'm dividing and then I add. So again, they're not reversing the order. Inverse means opposite, so therefore everything should be opposite about these two. So let's go ahead and let's try another sheet. Here we go. So one of the first questions you may ask is what happens if I have a negative? So what we notice is that here with the x, I'm multiplying by 5 and dividing by 3. Well, on the other one, I'm doing the opposite. I'm multiplying by 3 and dividing by 5. So far, this looks like the inverse. But does the negative affect my value? Well, if this is a negative times x, that's also a negative times x. Is there something other than a negative? Shouldn't I multiply that by a positive if I really want to invert it? Well, let's go ahead and plug this in to find out. So if I have an f of g of x, I have a negative 5/3 x, which means my negative 5/3, I'm going to leave a bunch of space right there and plug in my negative 3/5. We see the fact that not only do the 3's and the 5's cancel out, but my two negatives also do. So the key feature right here, f of g of x, is the fact that the negatives, if one is negative, the other must be negative. Just like what we didn't think about was if this was a positive, that was also a positive, nothing was the matter. So negatives work just the same. So my f of g of x works, and I betcha if we plug in the g of f of x, we're going to get the same thing. So negative 3/5, leave a big old set of parentheses, for my negative 5/3 x. Again, the 5's and the 3's cancel out, and so do the negatives. So my g of f of x also works. So they are each other's inverse. Awesome. So now that you've got some weight under your belt, let's go ahead and try a few more. I want you to try numbers 11, 13, and 15. Pause the video, see how well you do. Okay, so let's take a look. For this one, we notice, okay, so it looks like I've got more than one operation, so let's take a peek. If I were to follow my x from inside out, it looks like I am negating it. So let's write this down. I'm going to multiply. Then what it looks like I'm going to do is I'm going to add. So multiply, add, and then I'm going to divide. So what I'm expecting to see is I'm expecting to see that in reverse. So if I go down here, it looks like I add, and then it looks like I multiply. So we're really confused because this doesn't seem to have the same number of steps. But if I take that negative out there and break that into 2, that would mean that I multiply and I multiply. So this doesn't look good because this doesn't look like it's the same set of operations in reverse. If anything, it looks like if I ignore that negative, let's say move that negative down here, that would mean that that would become a positive x minus 7 over negative 2, which would mean I would subtract and then I would divide. Here I would add and a multiply. So we already know that this is probably going to be a no. But let's go ahead and find out. So my f of g of x is a negative x plus 7 all over 2. So negative, leave some room. And that's going to be a negative 2x plus 7. Okay. So when I multiply that negative in, sorry, I paused for a second. Multiply that negative in, that's going to give me a 2x minus 7 plus 7 all over 2. So work it out, the minus 7 plus 7 is going to cancel out, so I have a 2x over 2, which is an x. So f of g of x. So lo and behold, that actually does check out. So even though it was a little misleading, it looked like we added and then we multiplied. Same thing right here, it looked like we added and then we multiplied. They ended up working out. Let's double check, make sure we did that right. So I have a negative x, of which I plugged in a negative 2x. Oh, negative 2x plus 7. Yeah, so what we're going to have to do here, let's go ahead and let's cover some of this up. And let's say that that was actually a f of g of x is equal to a negative negative 2x plus 7. So unfortunately, I tried to write too small and I forgot the set of parentheses. So negative, negative, that's going to give me a 2 times x plus 7 plus 7. If I distribute that in, that's a 2x plus 14 plus 7 over 2, which is a 2x plus 21 over 2, which we can see is not going. Again, not sure what's going on with my handwriting, but the idea is that we know that this is not going in the direction of being an inverse. And if we flip it, G is not an inverse of F, but there's still a hope the other way around. F could be the inverse of G. Let's write our G of X. So negative 2, x plus 7, which is negative 2. Leave a big old space right here, plus 7. I'm going to plug in my f of x, so negative x plus 7 over 2, and we're going to solve it. So negative 2 times this, which means that's going to be a negative 1 times negative x plus 7, and that's going to be a minus 14. That's going to leave me, if I distribute that in, x minus 7 minus 14, so x minus 21. So we can see right here that neither are each other's inverse. So go ahead and ignore what we wrote right here and just make sure that we include the parentheses there. Awesome. Okay, and so let's take another look right here. If we know this is neither, let's take a look at number 13. Now again, it always helps to kind of work our way through. So we said that this didn't look right because it's going to be, we said if we move that negative down, it was subtraction then division, so SD. Down here, it was addition and multiplication. They're in the same order. Here, if I move that negative down, let's just go ahead and assume that at first. So that's going to be an x plus 3 over negative 7. This allows us to kind of compare apples to apples. So it looks like I'm adding and then I'm dividing. So step 1, step 2. Right here, what it looks like I'm doing is I am multiplying and then I'm subtracting. Again, we notice that if I go in reverse order, division, multiplication, addition, subtraction, this looks like this should work. So let's give it a shot. So f of g of x, take my f of x, so negative x minus 3, negative, big old set of parentheses. Make sure I don't forget any parentheses right now. 7x minus 3. Nope, didn't forget any. So negative distributed in will give me a 7x plus 3 minus 3 over 7. Notice those cancel out, so 7x over 7 is x. So that checks out. So G is an inverse of F. Let's try the other way around. Let's see if F is the inverse of G. A big old set of parentheses to plug this guy in. And so we see that cancels out, but I leave a negative. So negative x minus 3 minus 3. Distribute that negative in. So I get a x plus 3 minus 3, which leads me to an x. So we're going to abbreviate this because we're running a room, each other's inverse. However, you may know that each other is actually EO. Boom. There we go. Now the last one you may have had a little bit of fun with. This last one is a quadratic, and we haven't quite seen one of those yet. So let's go ahead and take a look and say, okay, if I follow order of operations following my x out, it looks like I'm adding and then I'm powering, or I guess what I should say is I am exponenting. Adding and then doing the exponent. Here, it looks like I'm rooting, which is another way of saying an exponent. We'll learn about that later on, how that's still an exponent. And then I'm subtracting. So we know that cool, different order, different operations. So this looks like it should be good. But let's pause real quick. Let's try it out. So my f of x is x plus 2 squared. So I'm going to leave some big old room right here for my square root of x minus 2. I know there's nothing to distribute here, so that's going to be square root of x minus 2 plus 2, which is just the square root of x squared, which leaves me with an x. So that's good. G is the inverse of f. Let's go ahead and check to see if f is the inverse of g. Put some room right here. X plus 2 squared. Okay, so our first step is we notice that the square root and the square are going to go ahead and cancel out. So we have x plus 2 minus 2, and this leaves me with an x. So g of f of x. Boom. So we have that right there. And so what this looks like is this looks like that they are inverses of each other. And to an extent, this is true. So each other's inverse. But in fact, in one of the next few videos, we're going to see that, albeit that this is true, there are some exceptions and some limitations that we're going to have to put in to make this always true. Because unfortunately, this is going to be one of those special cases where it's not always true. So today we're going to be restricting our domain. Now, the idea of what we're going to do here is based off of this concept. So let's take a brief aside. Let's actually move this out of the way. And let's see what we're doing. So certain functions, certain repetitive functions. Let's say that I have a sample graph with my y and my x-axis, and my graph does this. It keeps going, it keeps looping, 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 looping. What I know is that if I take the inverse, well, I'm going to have to swap the x and the y. So let's take a look at how that would look. So my new x and my new y. Okay. So as x is approaching infinity, y is approaching negative. So that would mean that as y is approaching infinity, x is approaching negative. So it's going to start out like this. Should have drawn my graph a little bigger. So foop, foop, foop. We notice is that we literally flip the graph over, and we'll get a rough shape that looks roughly the same. And we see the fact that, albeit that this one is a function because of the vertical line test. At any point we go along this, it only touches my red graph once. But unfortunately, when we take the inverse is not a function, so it doesn't work. So how do we fix that? Well, one of the things that we're going to do is we're going to find that at certain points, if we limit the domain, let's say if I limit it from here to here, and I draw some vertical lines, and I only take the area between. I only take that part of the graph. Well, let's see. Slightly positive to largely positive on the x. So I'm going to say slightly positive, which in this case I guess should have been right here. So largely positive on the y. I'll take that area right there, which means that through this little piece, our function actually works. So if I start here and only assume that that's that little area, I don't actually touch the function more than once. So boom, we've created a function. Now, the hot points is that we're going to use what we call local maxima and minima, which another word for those is we're going to use our vertices. The extreme low point and the extreme high point on each one of these so that we can invert it into something that works. Specifically, we're going to do that with quadratics. So if we take the same idea with a quadratic, x, y, new x, new y, and we take a quadratic. Let's give a quadratic right here. So I know that all along this graph, this works as a function. But unfortunately, when I flip it, so I have a positive y, it keeps going up. So I'm going to have a positive x, it keeps going up. Now, if I were to take this graph and do my vertical line test, what we notice is that if I only had one side or the other of this graph, this would work. And so that means we're going to have to find our vertex, draw a line through it, and pick, do we want the right side or do we want the left side? If we pick, let's say, for example, the right side, that means I'm picking all the positive x's, which means that right here, we're going to assume that that's my vertex, because it should have been the same on both of them. Positive x's, which means positive y's. And if I'm only concerned with the part of my graph that's up here on the positive side, all of that is a function. And so that is the concept of what we're doing today, is how do we limit our original function so that when we invert it, we get an actual function. Let's take a look at how we're going to do that. So we got 3 steps. Find the vertex either using the transformation rules or by visiting the formula. We're going to pick right or left. Now, today what we're going to be doing is arbitrarily picking a side. We're either going to pick right side or left side. Today does not matter. However, when you actually put this into application, or when you actually put this into use, normally in like your calculus class or pre-calculus class, it does matter. But for today, we're arbitrarily limiting the domain so that when we invert it, it becomes a function. Boop, and then we'll inverse it. So let's go ahead and put those skills to the test. First off, this function is written in vertex form. So I know the fact that x minus 4 means it's moved to the right by 4, no plus or minus. So my vertex is at 4, 0. So that's step 1. Check. Step 2 is we're going to arbitrarily pick a side to the right of the vertex or to the left of the vertex. Like we said, today it doesn't matter. So we're going to arbitrarily say x can be anything greater than or equal to 4. Check. We arbitrarily picked a side. The last step is we're going to inverse the function. So we're going to rewrite it right here. Step 3. I know that is going to be a y equals x minus 4 squared. And I'm going to solve for x, which means I need to do a couple things. We are going to, at first, square root both sides. And we know that when we take the square root, we have to take both the positive and the negative. And then we're going to add 4 to both sides. Now we have both the positive and the negative square root of y. That is not inside the radical, so I'm going to put my plus 4 on the outside. And this is our answer. But wait, positive and negative radicals. What that means is I have both sides of my parabola still. So let's take a look. If we say, let's draw a sketch of our graph, and I think we originally did red as our original. So we know our vertex has moved to the right by 4. So a good sketch would look something like this. Now we arbitrarily picked x values greater than or equal to 4. So we picked this point and we said, hey, only use this part of the function. Only use the right half, which means positive x's. So if I flip it and invert it, see this point is now on the y-axis. Awesome. So if we said only use positive x values, let's only use positive y values. So I'm only going to use that part of the inverted function. So we have that part and that part. Probably should have curved that a little farther so the arrows weren't right on top of each other, which means that if I'm only looking at the top half of the graph, I'm not actually looking at the negative piece. Let's do a color we haven't used. Let's do purple, which means we're going to get rid of the negative. I'm just going to circle that so that we know that we're getting rid of the negative, which means that our true inverted function is just the positive Awesome. So we allowed our function to be an inverse, like this. And I guess actually if we were to put it in function notation, this would be an f negative 1 of x is equal to the positive square root of x plus 4. I guess you could say that is actually our inverse function. And that would be our blue graph right there. Awesome. So what happens, you might ask, is if we pick the other side? Well, let's do another one. Let's take a look at number 3. So our first step is we find the vertex. This is a -4. We know -4 in vertex form means it's moved down. So it's at 0, -4. Let's pick the other side. Instead of greater than or equal to 4, let's pick less than or equal to 0. Remember again, we're using the x value as for our left or our right side. So if I pick the left side, let's see what we would do as we invert this. So y equals x squared minus 4. So my first step is add 4. Those go away. So I have y plus 4 is x squared. To get rid of that, I take the square root with both the positive and the negative. Awesome. And so what we know is the fact that with this, if I'm taking the left side of the graph, I'm getting rid of the positive. I'm only dealing with the negative square root of y plus 4. Which means that my true function is negative square root of x plus 4. Actually, I'm just going to box that one up. So there's my true inverse. Awesome. So my true inverse function is going to be the negative on this aspect. So let's draw that quick sketch again. So we know the fact that this is a quadratic that curves up, but it starts a little below the axis. So shloop and shloop. We know we're dealing with arbitrarily the left-hand side. So I'm going to go ahead and I'm going to darken this right here. Just like that, which means I'm only dealing with x as it gets negative. So if I invert this and take my x's and make them y's, that's a negative y, which means that's going to be a negative x. And I'm going to redraw. Again, I'm going to pass my arrow this time. I'm only dealing with negative x's, which means that as we invert it, I'm only going to be dealing with negative y's. Awesome. So we notice that, boom, yes, and it does look better once we cross the arrows like this. So we have our inverse function because we've allowed it to only accept one side of the equation. So perfect. So I think we've got the good idea. Let's try two more, but instead of sketching it, let's take it out of vertex form and let's plug it into just regular standard form. So for regular standard form, finding the vertex is a little different. We're going to have to take the negative b over 2a approach. So that's going to mean it's going to be a negative. My b in this case is 4. My a is 1. So let's see, that's negative 4 divided by 2 or negative 2. Okay? So I could keep going to find my vertex, which would be handy, but really all I need is that, because if that is my x value, because x equals negative b over 2a, that's all I need for step 2. I know that x either has to be greater than or less than that value. So let's pick arbitrarily the positive side. We'll try the negative side on the next one. So x is greater than 2. I need to find, okay, find the inverse. Which means y equals x squared plus 4x plus 3. So go ahead, take a shot, and see if you can't find the inverse of this function. Well, what you may have run into here is you may have run into the fact that, well, you have x in more than one spot, and, well, trying to isolate these x's, I could move the 3, but then I would have to factor an x, and I could divide out the binomial, but I would still have an x on the other side. So we're going to have to come up with a different set of rules. Well, a quick and easy way would be, this looks like a quadratic. So let's say this were a number. Let's say this were a 0. How would we solve this quadratic if that was 0? Well, we'd use the quadratic formula. But this isn't set equal to 0. Well, that's very easily fixed. The best way to set that equal to 0 is to subtract a y. What's that do? Boom. Set equal to y, x squared, x plus 3 minus y. Then you might ask, well, that doesn't look like any quadratic we've ever solved, and albeit you would be right up to this point, but the process is going to be the same. You have your a, your b, and the c is still the number without an x. So albeit even though your c isn't a number, it is now a binomial. You can still plug that into the formula. So if our formula is going to be x equals negative b plus or minus the square root of b squared minus 4ac, extend that a little bit further, all over 2a. So negative b squared, 4 times a times c, 2a. We see that it doesn't look any different than what we've been doing. The only thing that we'll have to pay attention to is the fact that we said we arbitrarily picked the positive side. So don't forget, with this, we're going to arbitrarily pick the positive. Let's go ahead and start working this out. In fact, actually, take a few seconds now. If you were confused earlier, see if you can't pause the video and finish this. But we're going to press forward. Okay. So leaves me with a negative 4. We arbitrarily picked the positive side. Let's see, 4 squared is 16. Let's see, that right there, 4 times 1 is 4, and I have to distribute that. So negative 4 times 3 is negative 12. Negative 4 times negative y is positive 4y. All of that is beneath the radical, all over 2. And if we work this out, we know that x is equal to negative 4 plus, well, 16 minus 12 is 4 plus 4y, all over 2. And again, we may have gotten stuck right here because we noticed that, hey, this isn't an expression that I can take the square root of. This isn't a normal type of radical. And again, you would be right, but what we notice is, what do both terms have in common? Both terms have a 4. And can we take the square root of 4? Yes, we can. So let's see how we would set that up. How about that? We factor out a 4. Now we know that this is the same thing as the square root of 4 times the square root of 1 plus y. And what is the square root of 4? 2. Perfect. 2, square root of 1 plus y, all over 2. Now we can actually reduce. So negative 2 plus 2 divided by 2 is 1. So square root of 1 plus y. And if we rearrange this so that it looks a little more familiar, we're going to put the radical first. So x equals the square root. And I'm going to list the variable first. So y plus 1 minus 2. So there's my equation. There's my function. Perfect. So now that you've gotten a taste for that, why don't you try number 7 real quick? Go leave both on the screen. Go ahead, pause your video, try out number 7, and see if you can't emulate this process. The big step right here, let's actually write a note. Try to factor out a perfect square. So once you've combined everything in the radical, see if you can't factor out a perfect square. Here, the perfect square is 4. Whatever you get inside that radical, see if you can't factor out a perfect square so that you can pull that outside of the radical. Okay, so let's take a look at what we got. 1, I know my vertex. I need to find out where that is. And that's going to be at x equals negative b over 2a. So negative something over 2 times something. My b in this case is 8. My a is 1. So that's negative 8 over 2, which is negative 4. Again, we could find the y value of the vertex, but we're not too concerned with that. And we said that because we arbitrarily picked the right, we're going to arbitrarily pick the left of this one. So less than or equal to negative 4. And that sets us right up for this. We say y equals x squared plus 8x plus 6. We said if only that was equal to 0, so we make it equal to 0. So we subtract the y from over there. 0 equals x squared plus 8x plus 6 minus y. And so at this point, we say, hey, we've identified our a and our b in front of the x squared in front of the x, and whatever's left is our c. So x equals negative b plus or minus the square root of b squared minus 4a, big room for c, all rooted and all over 2 times a. Plug in our b here and here. Plug in our a here and here. And plug in our c there. We also know that we arbitrarily picked the left side, which means we're going to pick the minus. So x equals -8 minus 64. Let's see, that's a -4 distributed in, so -4 times 6 is -24. -4 times -y is positive 4y. Combine these two, we get x equals -8 minus 64 minus 24 is 40 plus 4y. And remember, we want to see if we can't factor out a perfect square so that we can get rid of that. Well, it looks like it's going to be 4 again. So x equals -8 minus 4 times 10 plus y. We know that that's going to be the square root of 4 times the square root of that. So x equals -8 minus square root of 4 is 2. 10 plus y. Divide both those numbers by 2. So -4 minus 10 plus y. And then we rewrite it in a form we're more familiar with the negative square root y plus 10 minus 4. So there's the equation. F -1 of x. The inverse function is right there. Boom. And there we go.